Hello everybody, welcome to the monthly public talk series of IEEE Women in Engineering Affinity Group Albuquerque section. And I'm Aisha. I'm the chair of the IEEE Women in Engineering Affinity Group Albuquerque section. Today, Dr. Heinzelman, Dean of the Edmund A. Hajim School of Engineering and Applied Sciences at the University of Rochester, is joining us as our keynote speaker. As Dean, Dr. Heinzelman oversees a variety of programs, departments, and institutes that supports an undergraduate student body of 1,800 students, along with 120 faculty, 65 staff, 660 graduate students, and more than 20,000 alumni. She is also an accomplished researcher in the field of wireless communications, with her research supported by over 11 million in grants and published in over 150 textbooks, journals, and conference papers that have been cited over 50,000 times. What an amazing and inspiring bio. Thank you so much, Dr. Heinzelman, for making some time to join us and share your journey with us. Today with us, we also have our Affinity Group advisor, Dr. Tsiropolo, who I will request to say some words before we begin our talk.
Sure. Thank you, Aisha. And thank you, Wendy. I think it's both a great pleasure, but also an honor to having you today here, give us a talk. So I will say very few words. So I don't really know Wendy very well, but I met her in a recent conference at ICC. And, you know, some people are very bright, and when you discuss with them, you feel very being supported and being inspired. And in this group, what we really try to do is to inspire our students for their career paths. We are in New Mexico, and we are a relatively small university, so I think that bringing some speakers like you, it's quite helpful for our students. And thank you very much for that. Yeah, and I can't wait to attend the talk here.
Great. Well, thank you both very much. Thank you, Aisha. Thank you, Irene. It's, like I said, it's a pleasure to be invited. And what I thought I would do is just talk a little bit about my research area and some of the things, some of the sort of how I got to where I am, and what I've seen, sort of how the field has evolved. And then in the end, I'm going to talk a little bit about what I think is needed sort of moving forward. And then I'll try and end early enough that I'm happy to answer any questions, or if anyone has questions during the talk, feel free to interrupt me. I'm happy to answer questions along the way. So basically, I have been working in the field of sensor networks for over 20 years now. I started as part of my PhD thesis exploring this area. And you know what? I always start with a little bit of a motivation for why should we care about sensor networks, which, by the way, now most people call it Internet of Things, but I grew up in the era when it was called wireless sensor networks, so I still have a hard time switching the lingo to Internet of Things, but it's basically the same thing. And there's just so many applications of wireless sensor networks, Internet of Things, that really are going to be and are transforming everyday life. And so I'm just going to give a few examples, but health monitoring is one where we see a lot of benefit of using sensors to basically gather personal health information. And this can be for the purposes of disease monitoring or therapeutics, or for example, you can see here when you combine sensors on the body with sensors in the home, they can be helpful for ensuring that patients are safe and healthy as they go home, as they leave the hospital. So having these types of networks enables us to get much more personalized information, so we can treat people more specifically for their disease, for their particular genes, and how we can best help people. But it also allows us to increase mobility, increase independence of people in ways that was never before possible. I mean, it's sort of like, those of you who are older might remember there used to be that commercial, I've fallen and I can't get up, and the woman had like something around her neck and she could hit a button and people would come and help her. It's sort of the evolution of that. of we want to enable people to live longer in their homes independently or return from the hospital to their homes, but yet at the same time be safe. So a lot of really interesting applications in the health monitoring space. Similarly, environmental monitoring has a lot of potential applications, applications for monitoring air quality, water quality, monitoring everything that sort of goes on in the environment to try and understand impacts, for example, of climate change, to be able to figure out what it is we should be doing to protect our environment and to understand how our environment is evolving, how it is changing in relation to things like climate change, but also things like pollution. We can monitor and measure with sensors pollutants in the area and figure out how that relates to what's going on. Structural integrity, so we can put sensors in our infrastructure and our roads and our bridges to be able to hopefully determine that there are structural failures about to happen before they happen, so we don't get some of the catastrophic failures that we've seen over the last 50 years when bridges collapse, for example. Security, a lot of applications where we can better secure our perimeters, our houses, all sorts of areas by using wireless connected sensors. I always like this application of precision agriculture because I think it's a really good one of, can we do a better job of monitoring for things like moisture of the soil, for bugs and pests. So rather than watering every area that might not need it or spraying pesticides everywhere when they might not need it, we can be much more targeted in how we apply water, apply pesticides, apply fertilization to the soil, to the plants, so that we get the most food production that we can get. And there's a number of companies who are doing this currently. Vehicular sensor networks is another area where when we can connect our cars to infrastructure, and we see this all the time now, all of the new cars have the ability to gather information. They have a number of sensors in the car that are networked in the car, that are networked outside of the car, and that allows us to do many more applications with our cars. So, that's just a couple of examples. There's many examples of how we can use Internet of Things, wireless sensor networks. But I wanted to start with a little bit of history of where these things came from. So people have been networking sensors. Sensors have been around, forever, hundreds of years. And people started really thinking about connecting the sensors, networking them, getting the information between them around the 70s. 1970s. So back then, they were small scale systems, very large, power hungry sensors. It was always wired implementations. And it was primarily for machine monitoring. Things like you have these big giant machines, you want to be able to determine if there are parts that are going to fail. So you put these sensors in there and they gave you some information. And then research into the current day large-scale, low-power wireless sensor networks really began in the mid-90s and exploded in the early 2000s. And why this sort of came about was there were a lot of advances around the 90s and early 2000s, advances in radio or communication efficiency. We could much better get information wirelessly from one device to another. We started thinking about the concept of mobile ad hoc networking, and there were a lot of protocols developed for mobile ad hoc networks. Embedded computing, pervasive computing became popular. We had suddenly MEMS devices, so integrated devices where we could integrate the sensor and the communication onto a single device. We thought more about, and we had advances in low power hardware, VLSI design, data mining and distributed detection and signal processing became really advanced during the 90s and early 2000s. And it was really this crossroads of the hardware as well as the software and algorithms coming together to lead to this area of wireless sensor networks. And so the earliest projects in wireless sensor networks really came from the military. So DARPA sponsored most of the early drivers for wireless sensor networks. There was a 1978 DARPA-sponsored project on distributed sensor nets, and then the one I'm most familiar with is the 1997 DARPA Information Science and Technology study that really said, this is an area we need to invest in, we need to develop, because there's a lot of potential in this space. And one of the first schools to really make an impact in wireless sensor networks was UCLA, which had the Wireless Integrated Network Sensors, or WINS project. I believe that started around 1993. And they were one of the first to say, we need to focus on developing low power electronics to create these sort of integrated wireless sensor devices. And then two other projects that started in the late 90s. One was at MIT called the Microamps project. And this is the one I was lucky enough to be involved with. So I started my PhD at MIT in 1995. And as I started, I was working with my advisor, who was the PI for the Microamps project. His name is Anantha Chandrakesan. And so he was a VLSI guy. So his whole goal was to develop a low power integrated sensing device that could also on chip do signal processing algorithms and networking. And he had a lot of innovations in the space of dynamic voltage scheduling. So you change the voltage based on what kind of speed you needed on your chip. He needed someone to look at the communications of these devices, and that's where I came in. So I was lucky enough to be at the start of when people were thinking about wireless protocols for these areas of wireless sensor networks. And then the other one that happened, the other project that happened around the same time was at Berkeley. They created essentially commercial hardware, these motes. The concept of motes came out of Berkeley. And why they were so powerful is because they developed an open source software called TinyOS. It was an operating system that you could use on these very resource limited devices. And combining this open software or open source software operating system that was easy to use with easily available commercial hardware that you could get access to meant that suddenly people had access to easily programmable full function devices that could enable them to do research and implement real systems. And so that was kind of a game changer for wireless sensor networks. And this is pretty old at this point, but Dario Pompili from Rutgers had put together this timeline of different motes that came about. So you can see that the WEC Smart Rock from UCLA was the first integrated wireless sensor mote that came out. And then there were tons of different iterations from different schools and different companies that came out over the next 10 years. And I'll just point out a couple in particular. One is in 2002, spec mote on a chip. You can see that's actually a finger. And that little thing on the finger, that little dust mote, was basically an entire integrated sensor and communication device. Now, it was a very simple sensor, and the communication was like a couple bits a second. So it was nothing high power, but it actually showed for the first time that in something that minuscule, you could sense data and transmit data and connect up these devices. And then there were various stages of Mica motes and Telos, a company that created these, and then the iMote. And now, and again, this is even still probably a couple years out of date. There's even more now, but the T-Mote Sky, the WASP Mote, Zolardia, Arduino, Mica, Mica 2, Mica Z. All of these are readily available platforms. You can buy them, you can play around with them, and that has been a complete game changer, because now anyone and everyone can develop applications for wireless sensor networks, and you can actually implement them. And I teach a class on wireless communications, and around 2010 we started adding in hardware labs where you could actually go and program the Arduinos or program the T-Mote Skies and get them connecting and talking. And it just, that was never possible in years prior. So that was hugely beneficial for the field. Now, why wireless sensor networks are challenging is because they're really resource limited. When you think about comparing your computer to what you get on a tiny mote, you have your sensor unit, your computing, your communication, your power unit. You have all the same units that you would have on a larger, more powerful device, but all of these are working at very resource constrained levels. So the goal is how do we use our resources, our limited resources, while figuring out what do we need to maintain the application quality of service, or QoS. So we've got limitations in bandwidth, how much data we can send between the devices. We've got a lot of energy limitations that we'll talk about, computation and memory resource limitations. So given these limitations, how do we design our system to be most efficient? And what I think was really interesting about wireless sensor networks, it was the first time that you started thinking about network systems as not being user driven. So up till that point, most systems that you networked on the internet, on cell phones, they were all had a user as the end point. And so you never kind of knew what was coming because it depended what the user did and what they decided that they wanted to do. With sensor networks, you have a little bit more determinism, because you know what you're sensing and you know how often you need to sense to be able to gather the information you need, and you know what the application requires. Now, what you don't know is what that sense data is going to look like, and how you make decisions based on what that sense data is. But it was a different mindset for how you design these systems. And the other thing that was really interesting about most of these systems is that the sensors and the CPU were actually not the drivers of the energy drain. The big drivers of energy drain are the radio. Transmit and receive on these devices take a huge amount of energy to operate. And so this led to an interesting concept of thinking about how do we minimize communication and utilize the sensors in the CPU more so that we can minimize our energy dissipation. We want almost all the time our radio to be in idle or sleep mode unless we have to transmit or receive. So how do we do that? There were some interesting protocol questions there. Now, we all know energy is actually abundant, right? We have lots of ways that we can get energy from the sun, from the wind, from the waves. There's a lot of potential sources of energy, and we've utilized this energy for years. So, you know, water wheels and windmills, and there's been a lot of ways that we have harvested energy for many, many years. But we've only over the last about 10 years did we start thinking about how do we utilize some of these sources of energy for wireless sensor networks. So rather than thinking about, you know, as I mentioned, we started by saying, how do we reduce the need for energy because we have such limited resources? Well, if we actually can utilize reusable energy sources, maybe we can think about our sensor networks differently. So people have started to think about, well, how do we capture solar or mechanical, vibrational movement, thermal, electromagnetic? There's different kinds of energy sources that we can actually capture to power our sensor devices. And then once we have these sorts of reusable energy sources, we need to be able to store it. And then you think about things like rechargeable batteries versus traditional capacitors or supercapacitors. You have to have ways of storing the energy efficiently, which rechargeable batteries are not very efficient, but things like supercapacitors are very efficient. You want to be able to store enough energy to run your system and figure out how to utilize that energy. So, you know, we now are moving into an era of thinking about how do we have self-powered wireless sensor networks? Because I would say in the early 2000s, mid 2000s, when we thought about sensor networks, it was really how do we make them last as long as possible before they're dead? And once they're dead, we either have to go and change their batteries or they're basically just no use anymore. Now we want to think about, okay, how do we ensure that these networks continue to operate for as long as possible? So the energy source is there, but it's going to be unreliable, erratic, intermittent. So how do we accurately model the harvesting process, and how do we create intelligent designs so we can do things like adaptive energy management? And so, for example, if you look at a model, a very simple model, you can see you have sun, you can get a solar array, you have your radio, maybe harvesting some radio waves, and you can utilize that to charge your energy buffer, a supercapacitor, or whatever you're using as your energy buffer. So you have energy going in and then energy coming out to run your radio, your controller, your sensor, all of those sorts of things. So once you have a model of this, now you can figure out how to create your system, optimize your system. And so this requires us to think about things like, how do we model medium access control, channel access, routing, energy arrival, energy consumption, so that we have these models and then we can develop smart systems and smart protocols. So just to give you an example, I worked on a project probably about 10 years ago now with a collaborator from Sri Lanka, where they had a problem, they have a continual problem of elephants that are wild elephants, but they come into the villages. And when they come into the villages, they ruin crops, they trample homes, they actually kill people. And so the project was aiming to say, well, can we understand the mobility of the elephants so that we can figure out ways to solve this human-elephant conflict? And so we developed a sensor node that could be worn on the by the elephant, and basically would be recharged from the movement of the elephant, because they create actually a lot of energy as they're moving. And so you can see an example here of when the elephant is sleeping, there's not much energy harvested. But when they're eating or bathing or walking, there is quite a bit of energy that you can harvest. And once you harvest that energy, then you can use it. And we were using it for getting location information. So the sensors were GPS sensors, and we would network these so that the elephants would exchange their locations with each other and eventually get to a base station at the edge of the forest where they were walking around. So this is just an example to show, you can actually get reasonable amounts of energy by going through something like this. But then if you're using a type of reusable energy that is not always going to be available. So for example, let's say you're using a solar cell, and you're going to have maybe some that are in the sun and some that are in the shade. When they're in the sun, the energy buffer is going to be filled up. When they're in the shade, you're not getting any energy. So how do we think about how we design our protocols and our algorithms so that we're basically trying as best we can to use the devices that have a lot of energy to save the energy on the devices that are, for example, in the shade? And so we had developed some approaches where you could think about a MIMO system and how many transmit and receive antennas you used, how you did the communication depended on whether the transmitter or receiver had more energy. Similarly, if you think about a routing protocol, you can figure out how to do your routing of your data so that you're routing using devices that have a lot of energy or that are currently getting a lot of energy versus devices that don't. So thinking about all these things is really important. And then, as things have sort of developed, now we have sensors that get any kind of information you can think about. We've got optical sensors, we've got acoustic sensors, temperature sensors, motion sensors, humidity, moisture, chemical, gas, flow, electric, magnetic, leaks, force, acceleration, every kind of sensor you can imagine. There's so many sensors that have now been deployed or could be deployed in the world, and they're all gathering a lot of data. And so when you think about all of, we just talked about the Internet of Things and sort of the evolution of these types of networks, of wireless sensor networks. Now we want to think about big data. And with all of this data, what does that mean? And how does that interface with the Internet of Things? So data science is a field that has really exploded over the last 5 years. And data science basically is, how do we understand and make sense of data? How do we use existing data and find patterns that are going to be valuable? So now with all of these sensor networks, we have much, much, much more data than we ever could have had in the past. How do we figure out how to manage that and how to make sense of that? And this slide actually is relatively old now, because as of this year, everyone knows what deep learning is. That was a term that really wasn't all that well known until last year when ChatGPT came out, and suddenly everyone was talking about deep learning. But, you know, we have this whole field of AI, and that's been around for many, many years. And a subset of that is machine learning, using the statistical tools to basically learn from data. And then deep learning is a subset that is essentially driven by neural nets. So if you look at the timing, just like we looked at the sort of history of wireless sensor networks, if we look at the history of data science and machine learning, artificial intelligence has been around forever. It started in sort of the 50s when people were thinking about how could you make machines that were as smart as humans. And then machine learning really picked up in the 80s and 90s and 2000s, and deep learning took off. Well, it started in 2010 and it really took off last year, and it will continue to be an important way of analyzing and understanding data. You know, and AI's had a really interesting history. That if you look back in the 1956, or Marvin Minsky's quote here in 1970, from 3 to 8 years, we'll have a machine with the general intelligence of an average human being. That was in 1970. And we're still very far, I would argue. Even systems like ChatGPT, GPT-4 are nowhere near the intelligence of an average human being. They're very good at what they do, but they lack significantly in terms of intelligence. And then in it's called the AI winter of 1973, people were saying, well, we've spent all this money on AI, we've got nothing to show for it. Maybe AI is a hoax, it's not going anywhere. And then all of that really changed, just like with wireless sensor networks, around the mid to late 90s, when we started seeing real applications that we could use of machine learning. And the first applications really were spam filtering for email, when we started saying, okay, we need some automated way to be able to separate out real email and spam email. And optical character recognition was one of the first uses of machine learning. So again, putting this all together, we have all these smart connected devices. We now have a lot of work on algorithm design. How do we think about our AI systems, our data science, our smart systems in a distributed manner? Because what we would like to do is figure out, we want to analyze all this data. We don't want to put all the data in a central place and analyze it. We want to figure out, how do we do as much as we can analysis of the data at the endpoint, so we don't have to transmit so much data back and forth. And that's really what this connection of Internet of Things and data sciences, and some people call this sensor data science. How do we think about doing data science in a more distributed environment versus what we've really been doing so far, which is all centralized? We do the training centrally, we do the analysis of the data all centrally. So that's sort of the history of wireless sensor networks, the history of AI and data science, and how they've come together. There's a lot of really interesting problems that I think are going to be helped along by wireless sensor networks and data science, and this conflagration, this combining of these two fields together. And I like this list. There's a bunch of lists of sort of grand challenges, but I like this. This is the NAE, the National Academy of Engineering, their list of 14 grand challenges for the 21st century. And they include things in the high level domain of sustainability, of health, of security, and the joy of living. And you can see the individual challenges that the NAE says these are things that we really need to solve as a society in the years coming up. And if you look at these in more detail, many of these are going to be addressed or further developed with the use of wireless sensor networks. So things like making solar energy economical, You can think about the sensors that you can use to help to detect where the sun is, to help move your solar panels around, to help you do a better job of capturing the solar rays. Enhancing virtual reality, that's going to use a lot of sensors and a lot of communicating sensors to be able to enhance virtual reality. Advancing health informatics, we already talked about healthcare and how using sensor networks is going to really improve healthcare. Restoring and improving urban infrastructure, again, structural analysis, we talked about how sensor networks are going to be really important in that domain. Providing access to clean water. There's a lot of projects in looking at how do you put sensors into the water to be able to monitor for pollutants and to understand how pollutants spread in water and things of this nature. Again, managing the nitrogen cycle and developing carbon sequestration methods, all approaches that can use sensors to understand our current environment and to help us figure out how to address and solve some of these problems moving forward. So I think this is a really great way to think about the importance of sensor networks. And I also like this plot here because it really does show, you know, our technology is advancing at such a fast pace these days. You know, it used to be 1,000 years before you had a technology generation. And then, you know, going from the stone and fire to writing was thousands of years. And then it became hundreds of years between the printing press and the optical lens being designed and developed. And then it became on the order of 20, 30 years, from telegraph to plastics to airplane. And then suddenly it was every 5 years, you're getting a new technology generation coming out. And now, again, I'll get back to ChatGPT. You think about ChatGPT came out in November last year, so exactly a year ago. And I think it was January or February that GPT-4 came out. So the pace of evolution of technology is so accelerated compared to what it has been for all of human history. So that means we need to educate the next generation to learn the fundamentals, to be creative, globally minded, analytical thinkers, but thinkers who are going to meet challenges we are yet to foresee, because it's going to be impossible for us to know now what those challenges are going to be 5 years from now. Technology is just changing so fast. So when we think about education, we really need to think about how do we teach the next generation? How do we teach our students the fundamentals that they can build on and teach them to essentially want to be lifelong learners? So one of our benefactors at the University of Rochester is George Eastman. And he has this quote that says, "The progress of the world depends almost entirely upon education." And I love this because I think this is so true, that so much can happen and move forward when we educate the next generation. So I'm a big proponent of having people think about their learning and their career as being lifelong learners. That when you go to college, when you go to graduate school, it's a fixed period of time and you're learning, and that's great, but you're not learning to learn everything you need to know. You're learning to basically learn how to learn and how to continue to learn and how to continue to evolve, because that is absolutely going to be necessary. It always was necessary, but I think with the pace of technology changes going so fast, it's more important now than it ever was in the past that you just continually learn. I also think experiential learning is incredibly important, and making sure our students have the opportunities to experience things and try things and fail and learn from that. That's another really important aspect. And then we also really need to address pipeline issues that engineering, computer science, our field, we have been doing a lot of work in this area, but there is still so much work to be done. We cannot solve the problems that face us today if we don't have representation from every aspect of society. And we need to do a better job of reaching out to women, to underrepresented minorities, to those from rural areas who don't know about the excitement and what they can do with engineering. So we really need to reach out in so many different areas. And Irini knows about Networking Women, which is a group that aims, has one of our goals is to basically expand the reach and encourage more women to enter into the field of networking and communications. And so if anyone is not aware of this group, would highly encourage you to join. We hold meetings at all of the major conferences in the area, and it's a great way to meet really wonderful women and men. We have men who attend our events as well, who are working in this field. It's a wonderful community. So I'm just going to finish to leave some time for questions, to just give a little bit more background about me and how I got to where I am. So my mother was a teacher, and she taught middle school science, and she taught at an inner city middle school. So she was teaching kids who a lot of them were immigrants. Their parents didn't even speak English. They didn't have always the best family situation. And what I learned from her is that teaching can have such an impact on the future of your students. So she taught me the importance of being a good teacher, the importance of sharing your knowledge and encouraging and exciting the next generation. My father was an engineer. And to be honest, I probably would not be an engineer if it was not for him, because I never would have known what engineering was, except for the fact that my dad was an engineer and encouraged me to go into this field. He worked for 40 years at Bell Labs, and he invented a lot of speech technology. So this is an example of, on the left is, he did some of the first text-to-speech synthesis work. And so you can see there some of the early work that they did in this area. And then the picture on the right, this is something that just totally inspired me when I was a kid. So probably when I was in 6th or 7th grade, my dad had an exhibit that was put at Epcot Center. And this was basically one of the first voice-enabled video games. So you picked up the phone, you can see my dad there's holding the phone, and it was called The Mouse in the Maze. So you told the mouse up, down, left, right. That's all you could say, up, down, left, right. And the mouse would move up, down, left, or right, and you had to get it through the maze to get the cheese. And so it just seemed like the coolest thing ever. And going to Epcot to see his work being featured there was really, and it left a big impression on me as a kid. And then I also saw his excitement with doing research. He collaborated with people from all over the world, and it just was something that inspired me to do what I did. So then I went on and got my bachelor's degree in electrical engineering from Cornell in '95. And as I said, then I went to get my PhD at MIT. So I was at MIT from '95 to 2000. And then I went straight from MIT to being a professor at the University of Rochester. And I served as assistant professor from 2001 to 2006, then associate, and then full professor. And along the way, I started getting into administration. And in 2008, I served as Dean of Graduate Studies, which meant I oversaw all of our PhD and master's students across art sciences and engineering. And then in 2016, I took on this role of Dean of the Hajim School of Engineering, and I've been serving in that role ever since. Just a little bit more personal information, and these pictures are really old, but I'm married. I have a son who is 20, so he is now a junior. He's studying mechanical engineering and in particular aerospace. And I have a daughter who's 18. She just started college, and she is studying to be a biomedical engineer, which was totally not something I expected from her. She never liked engineering, and then all of a sudden last minute decided she wanted to be an engineer, which made her mom really, really happy, but I tried not to show that. So we'll see where they end up. And outside of work, I'm a big proponent that you work hard and you play hard. It's really important to have a balance in life and to be really good and passionate and love what you do, but at the same time to leave time for family and friends and things that matter to you. And so what I love doing, my family and I, we travel all over the world. Every time I go to a conference, I usually bring my family with me, and we take a vacation afterwards. We sail. I like to run. We ski in the winter. love to bike, do a lot of hiking, a lot of outdoors things. So that's kind of what I do that keeps me sane. And with that, I'm happy to answer any questions people have. I can stop sharing.
Thank
Thank
you,
you so
Wendy.
much. Okay, everyone's excited, I think. Should I go first?
Sure, Aisha.
Okay, so I'm gonna start by saying that you have a very, very wonderful family. And with that, let me ask you a question. Since you had a very long journey, I want to ask you if you have observed any change in attitude or policies within the engineering industry that are fostering a more inclusive environment for women nowadays.
Yeah, I do think there's I think it's much more welcoming than it was in the past. And part of that is just more of a recognition that we need to be open to larger to diversity. I'll say. So when I first went to conferences, it was really a little disheartening because there were so few women at the conferences. You were, in a sea of men, which was in great men, nothing against men, but there were just so few role models and people that you could see and talk to, and even just little things about, oh, I'm pregnant, having a baby. How do I attend conferences when I have a baby? The things that it's really helpful to have other women to talk about. I think there's a lot more support now for these sorts of things. So IEEE conferences now have childcare where you can bring your child and know that you can still do what you want to do with your career and have a family. I think it's one of the reasons we started Networking Women was to provide this opportunity for women to hear from each other, to learn from each other. So there are groups like Networking Women in ComSoc. There is WISE, Women in Women in Communications Engineering, and that also has a similar goal to N2 Women, and N2 Women and WISE collaborate a lot. So there's a lot more support, I would say, for and recognition that we need to do more to welcome people into the field. It can be very intimidating to go to a conference, for example, where you feel like everyone knows each other and you feel like everyone is in the group, is in the inn, and you're not. That can be very intimidating. So we're doing a lot more, not just for women, but for men as well. There's a lot more young investigator, young professional programs to try and connect young professionals, people who are new to the field, to some of the luminaries in the area, to understand what the norms are, to become and feel a part of the societies, a part of the conferences. And I think that's really, really beneficial because a lot of it is just making sure people feel comfortable.
Okay, I think we have a question. Thank you so much. I think we have a question in the chat. So Salman says, I wanted to ask you what initiatives or strategies do you believe are effective in promoting diversity and inclusion within the field of engineering, particularly for women?
Yeah, I think all the things that I was talking about, I think making women feel welcome in the field is really important. And how do you do that? Well, including people just the same way you make men feel welcome, right? You include them, you introduce them to people, you make them feel a part of the field. I think also one of the things that I try to do with my own students here at the University of Rochester is talk about engineering in a different way. So traditionally, people have this vision of an engineer as someone who is very solitary, sits behind a computer, not very social. That's the sort of what's the word, cultural vision that you have of an engineer. And you don't think of engineers as sort of being the people who are changing society for the better, where you think of doctors, right? Doctors, everyone says, oh yes, if you're a doctor, you're making your impact on society. And so doctors didn't used to be many women. It's 50% women now, over 50% women. Doctors, the medical profession has completely transformed. And a lot of it was women really want to, in general, want to have impact and want to know that their work has impact. And so I think talking about engineering a little bit differently. So instead of saying, oh, do you want to be an electrical engineer? And people saying, I don't even know what that is, to say, hey, do you want to work on problems that are going to help ensure everyone on the planet has access to clean water? Okay, if you do, in what way do you want to work on that problem? And how can we work together? And let's talk about teamwork, and let's talk about communication and some of these other skills that are really important to be a successful and a good engineer and a computer scientist. Changing that conversation so it's not about, okay, you're going to be stuck behind a computer not doing anything that's going to have value. I wouldn't say that. I think people always realize engineers have value, but not necessarily doing something that is going to help people in the long run. To what can you do? What do you want to do to help people? And how do we use engineering to help you achieve your goals? I think changing the conversation in that way can be very helpful.
Thank you so much. Do we have any other questions? If anyone has any questions, feel free to unmute yourself or write it down in the chat.
I think the talk was very informative, and actually I enjoyed especially the second part, to be honest. I liked it very much that you mentioned the End to Women. It's actually a great organization, and now that you were talking, I thought back and I'm like, this society, it's the one that felt me comfortable when I started attending the conferences. So yeah, I just flashed back.
Yeah, and actually when we started this, I was part of not just ComSoc, but also Signal Processing Society, and I would attend ICASP as their flagship conference. And ICASP would have, at every ICASP, they had a women in signal processing lunch. And I thought it was just the coolest thing. As a graduate student, I was sitting next to some of the luminary women. There weren't many, it was a small room, but I was having lunch with the luminaries in signal processing, and I thought it was so cool. And so that's really what led to N2 Women starting up. So it was signal processing was the ones who actually started that concept, and it just, to me, it just made such a difference and had such an impact. So I'm glad to hear you felt the same.
Yeah.
Okay, we have another question. Yisheng says, hi, Professor Heinzelman. What's the most difficult course for you during your PhD in MIT?
Probably, so I did a math minor, and those were my most difficult classes. I would say probably chaos theory. I took a class on chaos theory, and that I'm not sure I ever really got. It was very interesting. Someone named Strogatz, Stephen Strogatz, taught the class. He's got a famous book. So I was like learning from the person to teach and talk about chaos theory, but I'm not sure I ever really got it.
I hope Yisheng is going to remember that.
Yeah. Then again, I don't think I've ever used chaos theory, so it hasn't hurt me too badly.
Okay, so let's see if anyone has any other questions. Did you have any female professor instructor in MIT?
I hope the answer is yes.
During your PhD years?
Nope. The only, actually, even in my undergrad years, I had one instructor undergrad, Sheila Hamami. She came, I was at Cornell undergrad. She came my senior year, and she taught a seminar course. So I decided to take the seminar course just so I could have a female professor. She was wonderful. So I did take one class at Cornell with a female professor. I had no one at MIT when I was leaving, or not when I was leaving. She came before I left, but I had stopped taking classes. Muriel Madad, who some of you may know that name, she works in more on information theory side of communications, but she came to MIT like at the end of the 90s. So I wasn't taking classes at the time. So no, I didn't take a single class with a female instructor at MIT. There were a couple female professors. Dresselhaus, Mildred Dresselhaus, who's very famous, was there. And Barbara Liskoff in computer science. She's also very famous. She was there, but I didn't have classes. I think those might have been the only two women in EECS when I was there.
Wow, I've never thought that there were so few.
I mean, at Cornell, until Sheila Hamami came, there were none. And like I said, MIT had, I'm pretty sure it was 2.
I hope the situation is better now.
That has changed.
Okay, I think Aisha, you can conclude the presentation and the talk for today.
Yeah. I think it's getting pretty late over there for you, Dr. Heinzelman. What time is it over there?
Yeah, it's almost 8.
Oh my God. Okay, so let's say good night to everyone. Thank you so much, Dr. Heinzelman, for having some time to join us. It was a very informative talk. And today's meeting was recorded, and I will be uploading it in our YouTube channel, and I will share it with you in case you would like to have a copy of it. Thank you so much once again. And thank you, everyone, for joining us.
Thank you. It was a pleasure.
Thank
It was
you.
a pleasure. Good night, everyone. Bye-bye.